So, first of all, I would like to thank Davide and the local organizer because they really did the big job here, so I did nothing, essentially. And so the new title is Irrelevant Perturbation of Two-Dimensional Integrable Model. So seems to be fairly active research field at the moment because there are people coming from different communities, starting from entanglement theory, string theory, ADS-CFT, well, of course, integrability, but also some people interested in simulation of lattice QCD are interested because there is a relation between the flux tube connecting quark and antiquark and this Nambu-Goto theory. So this is a partial list of paper. I think this year there have been about 60 paper on the subject. So it's really, you see a lot of people here, including Miguel and Leonardo, which gave this very nice talk this morning. Okay. So why we are interested in study effective field theory? So we know that effective field theory, so non-renormalizable field theory, have problems. So we understood, we learned at the university there are problematic theory, but in two-dimension, integrability can help us to understand something, at least. I mean, not to solve all the problem, not to understand really non-renormalizable field theory, but at least to make some progress. So the first motivation came from discussion with Michele Caselle and Ferdinando Liozzi in Torino. They are very expert in simulation of Yang-Mills theory in 3 and 4 dimensions. And in that case, you know that they can study the interquark potential and the property of the flux tube joining a quark and an antiquark pair. Okay? And it is well known that this potential is very well described and also some excited state by the Nambu-Goto theory. So the Nambu-Goto theory is one of the theories which will emerge out of this discussion, as already mentioned by Stefano. Okay. In general, well, for example, Sasha Zamolodchikov is interested. I mean, he told me that he's interested in this stuff because he wants to understand the physical meaning of the singularity appearing when you study the renormalization group, or the TBA, the flux described by the TBA method or TBA equation. Okay, and in particular, what we discovered recently. I mean, it was roughly in the air since many years ago, but this new result really motivated people to study this model at the deeper level. Is a relation with between irrelevant perturbation and what we call the Cdd factor ambiguity when you study the exact scattering matrix in integrable model. Okay, so so exactness matrix means integrability, but we will see, and as already mentioned by Stefano, some of the results are actually universal. They don't need the final result equation are valid in general. They don't need integrability. Okay, so at least from my point of view, the old idea about renormalization group flow was that or at least in the integrable model setup, was that you were starting from a well-defined ultraviolet fixed point described by a conformal field theory, which I denoted simply just as CFT ultraviolet, and then you perturb it with a relevant operator. Okay? So in some cases, the theory becomes fully massive, so it flows to an infrared theory which is trivial. But in other cases, it remains at least it remains a subsector which is massless. Okay, so when this relevant operator drives you away, it goes to a fixed point in the infrared, which is non-trivial. So it's described by another conformal field theory, which is non-trivial. Okay? So integrability method, like the exact symmetric approach for this kind of massless theory, was were introduced by Alyosha Zamolodchikov many years ago. And in particular, he studied the first, a very simple model in which the ultraviolet theory is the tricritical Ising model, and the infrared theory is the Ising model itself. And there is a critical line connecting these two theories, and the S-matrix by Alyosha Zamolodchikov were describing exactly this massless flow along the critical line connecting these two models. Okay? So these are very powerful techniques. So from the S-matrix you can derive exact thermodynamic Bethe ansatz equation describing the energy level at final size, so at final volume. So you can vary the volume from very small to very large, and you essentially describe the theory like in the RG flow at small scale and large scale. Oh. I should go faster. No. Okay. So with this technique, we could study, understand the content of, understand what was the leading attracting operator in the infrared, and in some cases also the subleading attracting operator. But actually in physics, we are more interested in shooting back. So starting from a conformal field theory, which we think is describing the low energy property of the theory, and try to perturb it with an irrelevant operator. And we learn at the university that this is essentially hopeless, because as already mentioned by Stefano, we should include a correction. Every time we include a correction, we usually introduce a new free parameter, so it means that at the end we end up with a unfixed here with an infinite number of free parameters. Okay? However, integrability might help us to understand something. So integrability is stronger, and maybe the imposition of integrability can help us at least to study some of a subclass of this theory. Okay, let's go back to this Cdd factor ambiguity. So in general, we were used to study a theory, so to quantize a theory, trying to obtain the exact S-matrix of the theory. So essentially, if we have the exact S-matrix of the theory, we essentially quantize the full theory. So the idea is usually that you know the symmetry of your theory, and then if you understand that the theory is integrable, you have to solve some constraint, some strong constraint for the two-body scattering matrix. So theta is the rapidity, so the S-matrix for relativistic model would depend only on the difference of the rapidity of the particle. Okay? And these are the well-known Yang-Baxter equations that are really deeply related to integrability. And it's, from the point of view of the S-matrix, it's just factorization, it's just a factorization condition. It means that the n-body scattering matrix is just the product of two-body scattering matrices. Okay? Okay, suppose you have your Yang-Baxter equation with and then you impose some physical condition like unitarity for the S-matrix and crossing symmetry. And suppose you are able to solve this equation as we did, or in many cases, then you have a S-matrix model, so you can apply the bootstrap to understand what is the particle content of the whole theory, etc., etc. However, you have to do some assumption, to make some assumption about, or some minimality assumption on the S-matrix. So it means that you can always add a factor, multiply your S-matrix by a factor, which is a scalar factor, which fulfill trivially all these equations. So trivially the Yang-Baxter equation, and trivially unitarity and crossing symmetry. So this is the so-called Cdd ambiguity. Okay? We know some cases where two theories, completely different theories, are just related by a Cdd factor. So there are theories we know that are for which the S matrix is a pure Cdd factor. Okay? Or whether let's say the Cdd factor are complicated, so they, when you include them, they give contribution from many operators. But there is a very simple choice for the Cdd factor. So the simplest choice of Cdd factor is this one, where the phase shift in this phase factor here, it's a simple hyperbolic sign of this form. So remember that theta is the difference between the rapidity of the two particles, and there is a free parameter which I denoted tau, which has the opposite convention with the alpha for the sign with the alpha introduced by Stefano. Okay? So many people knew about this possibility already many years ago, but we discarded it simply because you expect the phase here to go to a constant value when at very high energy. Okay? However, this phase factor is actually growing with theta, so it's growing at high energy. So there is something unphysical that we don't really understand about this Cdd factor. However, we should be more brave in trying to understand what is the influence of this Cdd factor in a concrete example, to understand really if we are wasting time exploring this kind of equation. Okay? So you shouldn't be scared about this equation. So as I said, we develop a lot of powerful tools in integrable model. One tool is Yang-Baxter equation, S matrix approach, etc., etc. Once you have the full S matrix of the theory, there is a way, first introduced by Zamolodchikov, but then generalized by other people, to get the correction, the finite size correction of the spectrum of the theory. Okay? So this is an alternative equation compared to the TBA equation. It's very compact. This is valid only for the sine-Gordon model or closely related model. Okay? So you don't have to understand completely the origin of this equation, because, well, essentially it's coming from exact quantization condition using a Cauchy theorem and some Fourier transform. Okay? But you see, this equation is an equation in the unknown function f of theta, which we usually call counting function. So f of theta is the counting function. This is on the left. It's also appear under this convolution here on the right as an argument of the log. Okay? The first term on the right-hand side is proportional to the volume of your theory. So R is the circumference of the ring where you confine your theory. M is the mass. In this case, this is the mass of the soliton, because we are dealing with the sine-Gordon model. And so this term M sine of theta is essentially the bare momentum of the particle. Okay? And then this is a constant which is not play any particular role for the following discussion, is the twist parameter or quasi-momenta discussed by Lukyanov and Bajanov some days ago. Okay? And what about the remaining part? So the remaining parts essentially are the part that are dressing the bare energy of the bare momentum of the particle. So there are two convolutions here. along two different integration contours, but the kernel appearing here in this equation, it's essentially it's related, or it is the logarithmic derivative of the soliton-soliton scattering matrix. So it's a scalar function, it appears as a kernel. Okay? And then the contour of integration are running just above and just below the real axis, because on the real axis you have the branch point of the log, okay? And the branch point coincides with the Bethe-Ansatz root, okay? Already mentioned in the previous works, okay? So now suppose you have a solution of this equation, okay? Okay, I should also mention that you can also get information about excited state, but just simply formally by changing the contour integration and making them going around some singularity of the log. Okay? So in principle, generically speaking, this equation contains all the information, the exact information about the spectrum of the Sine-Gordon model at finite volume R. Okay? Now suppose you solve this equation, and you can do exactly only in particular cases, but you can solve them with very, very high precision, so arbitrary high precision, like 30 or 40 digit, you can calculate f. And then using the same equation, you can understand all the property of this scale, of this counting function in the complex plane, in the complex theta plane. Okay? Now suppose you have a solution of this equation, then you plug the solution f in these two expressions, and you get the total energy of the state and the total momentum of the state. Okay, now let's see what's happened if we include in the kernels, if you change the kernel by including the Cdd factor, which I introduced before. Okay, so so what we have to do is very clear. We have to change the kernel, modify the kernel in this way, including the logarithmic derivative of the phase factor I described before, and this is how the kernel gets changed. And if you plug this into the nonlinear integral equation, you immediately realize that the only thing is changing is the driving term. So it acquires two bits, both proportional to the parameter, to the perturbing parameter tau, one involving the energy of the state, and the other one is involving the momentum, the total momentum of the state. Okay? So suppose, for example, you want to discuss you are thinking about the ground state energy, so this P is equals 0. And you see the net effect of having introduced the Cdd factor is a change in the volume of your theory. So, so R is shifted by this parameter tau and a term which is E. So, and the rest is the same. Okay. Now there is a more convenient way to write this modified driving term, is that to reabsorb the two terms in a shift of the rapidity parameter of the hyperbolic sign, and in a redefinition of the volume of your system, which I denote as R0. Okay? And then the map between theta 0, R0, R, tau, and P is this one. But then this change of variable, its change of parameterization is useful because it tells you that the new counting function that depend in principle on tau is actually simply related by the undeformed counting function in this way. Okay? And there is a way actually to rewrite all these equations in a form which looks like Lorentz transformation. Okay, so for example, in general, this property is true. Okay. Now, all this equation together is actually not difficult to show that they give implicitly a solution of this generalized Bourgeois equation. Okay? So this is the generalized Bourgeois equation already introduced by Stefano this morning. Okay? So this is very nice for many reasons, because it's an exact evolution equation. It's an hydrodynamic type equation. It's actually the simplest hydrodynamic type equation which we exhibit the wave breaking mechanism or shock wave mechanism, or you want to call it. And it's a first order, so it's a first order differential equation. Is nonlinear because E appears here and also here. And the strange thing that is important to point out is that it relates this parameter tau to the geometry of the system, so to the circumference or volume of your system. Okay? So this is first order in tau. It means that you just need to impose initial boundary condition at, for example, tau equals 0, and this equation would evolve your state, your energy level at arbitrary tau. So this is the typical plot for the energy level, finite size energy level of an integrable model. This is actually, it's a free theory. It's the Ising model. A free Majorana fermion at finite volume R. Okay? So you see, these are the energy level as function of the parameter of the volume R of our system. Okay? So you see the blue line at the bottom, it's the ground state, correspond to the ground state energy, and it goes exponentially to 0 for a very large value of R. While if you are at R equals 0, you are exploring the ultraviolet property of your system, and this means essentially that close to this point, the theory is described by the underlying conformal field theory, the ultraviolet conformal field theory. So the behavior of actually all the level is of this form. So with the pole singularity at R equals 0. Okay? So now let's see. So this is the starting point, and now we use this condition to run the energy at tau different from 0. This is what you get. So for example, this is for C effective equal 1, so positive. So the picture is actually very general. Very universal. So this is the shape of the initial state, shape of the ground state. You see see here the pole, the singularity, and as soon as you tune on the parameter tau, this is very small. You see this energy. So this level here is bending toward the right of the figure, and so there is a formation of branch point here. Okay. So there is a formation of branch point of a square root branch point here, but also the other property is that you have a doubling of energy level. So there is something coming from minus infinity, very negative energy, and now become, well, it's a finite distance from the ground state energy. Okay. So if C effective is tend negative, like, for example, for the excited state we saw in the picture before, something else happened. So this is the original energy level. We think about it as an excited state in this case, and is actually bending toward the unphysical region, which is R negative, so negative volume. Okay? On the other hand, a state coming from the unphysical region, R negative, is moving on the physical region, which is R greater than 0. Okay? And even in this case, even if you don't see the merging of a square root singularity, you see the doubling of the energy levels. So this is, at least from the quantum field theory point of view, looks a bit strange. Maybe it's natural in string theory, but for us, I think looks a bit strange. Okay.
So you expect that state actually to be in the spectrum?
No, usually we don't consider it. Okay, so we only consider the original spectrum, so the deformation of the original spectrum.
Right.
Okay, so in string theory they also do like that. They have a spectrum with a square root. They only consider half of the spectrum. Okay, so this we'll see give us a spectrum which is identical formally to the Nambu-Goto theory. So we probably should do the same. Yeah. But then I understand that in this way you don't really understand the physics behind the emergence of these negative energy levels. Okay, so let's apply this technique to the simplest possible theory, which is a conformal field theory. So there is the theory is completely critical, is conformal. There are no scale at the beginning in the theory. Okay, so this theory, this limit can be obtained from our nonlinear integral equation by sending the mass of the soliton to 0, okay, and rescaling in some way, so it's a scaling limit, rescaling in some way the rapidity appearing in the nonlinear integral equation to either to infinity or to minus infinity. Okay, so in this limit you see that the energy level decouple in two sectors, so the right mover sector, so particle moving clockwise, and left mover sector, so particle moving, massless particle moving anti-clockwise. Okay, so the solution of our Bourgeois equation is this one. So it's actually so at tau equals 0 is the conformal spectrum, but at tau different from 0 is actually coupling the energy of the right mover sector to the energy of the left mover sector, and vice versa. And this is again true our definition of the volume which appear at the denominator. Okay? So these are simple algebraic equations. You can solve them, and this is what you can sum then the contribution from the right mover and left mover to get the total energy of the system. This is what you get. Okay? So it's amazing that this coincides with the result for the bosonic string theory, which is called the Nambu-Goto model in the critical dimension D, where the dimension D is related to the central charge CF. So in general, this result is for the Nambu-Goto theory is valid only in this critical dimension. So C effective is equal to 24, but actually the result here is independent on so it's valid for an arbitrary conformal field theory. Okay. And indeed, the inverse of the parameter tau is what is so-called string tension in string theory. Okay, now we have this Cdd factor. We understood that it's producing something interesting. Probably it's a new physics. It's some interesting result. Let's try to understand what is the operator associated to this Cdd factor. Okay, so there is a naive way to do that, and you start from your Bourgeois equation, which has this form, and then there is a well-known way to associate to the energy and the derivative of the energy with respect to R, the expectation value of the stress energy tensor. Okay, so in this way, and now in the following, I almost always use complex coordinate. So in complex coordinate, the entries of the stress energy tensor are t bar, t, and theta is essentially twice 1/2 the trace of the stress energy tensor. Okay? So now we just want to rewrite the right-hand side of this equation, and the result is this one. So the right-hand side of this equation is actually related to the expectation value of an operator. It's irrelevant operator, which is called, was denoted by Sasha Zamolodchikov TT bar operator. Essentially, it's the determinant of the stress energy tensor. So the TT bar operator is essentially is the determinant of the stress energy tensor, apart from maybe some normalization. Okay? And this operator, which, as I said, was introduced by Sasha Zamolodchikov, has some fantastic property, which is this factorization property. So the expectation value, as it was explained by Stefano this morning, the expectation value of over an arbitrary state n of this TT bar operator just factorized in this simple way. Okay? And this is why I wrote this formula, this equation here. Okay? So this is a special property which is in general not unique. So there are other composite operators, as we shall see, that have this property. Okay? So since the Bourgeois equation is valid for any energy level in the theory, you might think to build up, at least formally, the partition function. So the partition function would satisfy this equation here. So this is the partition function on the torus of lengths r and L, which depend, of course, depend on the parameter tau. No? So you have this equation. Now, if you think about the path integral formulation of this partition function, then you end up, you argue immediately that even also the Lagrangian, the classical Lagrangian, should satisfy a similar equation. Okay? So the derivative of the Lagrangian with respect to tau is nothing else than the determinant of the stress energy tensor. Okay? So now you have a scheme where you can produce new TT bar perturbed Lagrangian. So you start, for example, from the unperturbed Lagrangian, you calculate the stress energy tensor, you take the determinant, you add it to the Lagrangian. Now you have a new stress energy tensor, you calculated it, you added it to the Lagrangian, etc., in a perturbative way. Okay? And so this is the way we got our first result with Stefano and Andrea and Istvan. Okay? So suppose you start from a theory, a generic theory containing n boson. Okay? So this is the kinetic term, plus a potential which in general depend only on the field and not on derivative of the field. Okay? Now you apply this trick, there are other, so this perturbative trick, but there are now more clever way to arrive to the form Lagrangian. This is what you get. Okay? So you get again a square root singularity. So the square root here, the first factor here depends only on the potential, and there is also this tau parameter at denominator. And this B factor here is essentially this object. And inside you see this B factor here and the unperturbed Lagrangian L at tau equals 0. And you get this tau bar, which is actually a local actually to a local redefinition of the parameter tau. So depending on the potential V. Okay. So this looks as essentially this Lagrangian looks as it has some singularity due to a pole here probably due to this term here, and the square root singularity due to of course the square root there. Okay? So once you know the Lagrangian, you can do Legendre transform, and this is what you get for the Hamiltonian. Okay? Now, to make contact with what we obtained before, let's consider the case where V equals 0. This is then a conformal, the Lagrangian for a conformal field theory. So this term here disappears. Tau bar becomes equal to tau because this term here disappear, and you see this is exactly the form, but is a local form a local result matching the result we got at quantum level using the Berger equation for the conformal field theory. Okay, now let's go back to the Sine-Gordon model. So this result is very general. It's valid for an arbitrary potential and for this bosonic type theory, and there are generalizations also including fermions, supersymmetry, etc., etc. However, let's stay within the bosonic theory. So this is the Lagrangian that I wrote included this S factor, which is essentially the square root factor. And so there is only one boson, so this B factor is actually 0, is vanishing. And then the potential is the standard Sine-Gordon potential that I write in this way. Then once you know the Lagrangian, then you can, of course, calculate the equation of motion. Okay? And this is the result. Okay? This is also general because the V can be, okay, we'll study the Sine-Gordon model first, but actually these are very general for arbitrary potential V. So they are very complicated, and we try to solve initially this equation of motion in a perturbative way, to try to understand the shape of the solution, and we failed. Okay, apart from some very simple example like the King solution, the deformed King solution for the Sine-Gordon model. Okay, so we tried a more rigorous approach. So we tried to construct the Lax pair associated to this equation of motion, and we actually managed. Okay? So once you know the Lax pair, then we thought, okay, then we can understand the integrable structure of this theory. For example, we can construct the conserved charge of this theory, etc., etc. So we did many calculations, but at the end, we realized that there was a much simpler way to explain, much more cute way to explain our results. Okay? And this is through the map that was also mentioned by Stefano in this morning. Okay? So we found that there is actually a map which somehow trivializes the solution. So suppose you have a solution of this very messy equation of motion, which depend on tau. Then we found that the form equation is actually can be mapped into the original tau equals 0 equation, a bit like the Berger, what is doing the Berger equation for the energy levels. Okay. So, and however, this map is depending on the value of the field itself. So it's a local deformation of space-time. So you have two interpretations. Either you think about phi of tau as a solution, a complicated solution on a flat space, or on a simpler solution, the original one, but running on space-time deformed by the solution itself. So this really looks like a gravity-type theory. So there is no graviton, of course, but it's give us the idea of what's going on. So this is a theory in which your solution is deforming somehow from, at least for a certain point of view, your space-time. Okay? And the other, so this essentially means that this very complicated equation of motion become the free equation of motion when you perform this map in the new variable W, which are this modified, so this space-time, deformed space-time. So these are essentially the equation of motion, in this case of the Sine-Gordon model, but as I said, this is valid for an arbitrary potential V. Okay? So this give you a way to find the form solution in terms of the old unperturbed solution. Okay? So for example, this is the king solution. So this is what happened. So the king solution become flatter if you go to negative tau. So it's doing something like, so it starts from this, and if you go to negative tau, it goes like that. But as you increase tau instead, if for tau positive, then it becomes multivalued. So this is the shockwave phenomena, but a microscopic level. And actually the two phenomena, the one happening for the energy level and this one, are not correlated, are not related. Okay? Okay, that's the simplest example. We knew already by solving this complicated equation of motion and looking for a stationary solution or a solution, a very simple solution. You can do the same for other solution. We did it for the breeder solution, which is the bound state of the soliton-soliton, of a soliton and an anti-soliton. This is the stationary breeder solution, which of course depends on time because it's breeding. This is the solution, and this is the period of breeding. And you see, this is the undeformed solution. Okay, so this is the time, and this is the x direction. So it's breeding in time. And so if you decrease tau, so if tau is negative, then you see this bump here, this blob, they become wider and wider. Okay? At certain point they will touch and then intersect each other. Okay? So, but in any case, already at this point you see the solution is multivalued. Okay? So to plot this, we had to be, well, sufficiently clever. For positive tau, the inverse happens. So this blob here, the blobs, they are shrinking in this way. Okay, and again, at a certain point, they will touch each other and right to left or in this direction, and they will cross. So you will have an exact crossing because, of course, the theory is integrable. Okay. Okay, now we can put this in a general framework. So we have, this is the Jacobian of the transformation between the two variables. So the Z are the plane variable and the W are the deformed one. This is the Jacobian, and you see that on the diagonal you have a V, which is nothing else than the trace of the stress energy tensor, or half of the trace of the stress energy tensor. So the natural thing to do is to replace this V with theta. Okay? And in the off diagonal in this element, you recognize the T and the T bar. Okay? So in Euclidean coordinate, this is in the differential form, this is what we got. Okay? So now, so you see the change of variable depends on T, and T is essentially related, directly related to the stress energy tensor of your theory. So you are changing variable in a way which depend on the stress energy tensor. Okay? Now, if you stare at it, at this equation for 5 seconds, you say, oh, it would be nice to generalize this theory to so that to get some generalized type of gravity theory. So what can I replace this T, the stress energy tensor, with? And the answer is actually trivially simple. So you take second derivative, you start from this, you take second derivative, and you want to match the two second derivative in the variable y, and this gives you a very strong constraint. So you need to do this change of variable, you need that this T mu nu is conserved, as it is for the stress energy tensor. Okay? So, but okay, this simple observation allow you to generalize this construction to other conserved currents. Okay? So we know that for a free theory or for an integrable theory, you have an infinite tower of conserved currents. So not only the stress energy tensor, and in particular they are labeled by this Lorentz spin, which is S. So for S equals 0, this becomes the conservation of the stress energy tensor in complex coordinates. Okay. Now S in general is an integer. For the sine Gordon in general is an odd integer, but it can be positive and negative, both positive and negative. And actually from this point of view, from the conservation law, the negative spin are perfectly equivalent to the positive spin. However, there is an interchange of the trace of the stress energy tensor theta with t bar or vice versa. Okay, there is a little a little interchange between theta and t bar and t and theta bar, and this actually looks trivial at this level, but is actually important because in the Jacobian the two results will not be the same. Okay, so for us, from our point of view, from the point of view of the change of variable, positive spin S and negative spin S give rise to different and very different actually theories. Okay, so the idea is now to replace in this Jacobian the stress energy tensor T with some object built with the higher conserved currents, Ts. Okay. So concretely, what you can do is to replace the original Jacobian with this quantity here, containing now theta s minus 1, theta s plus 1, ts plus 1, etc., etc. So this is something natural to do in knowing that you have an infinite tower of conserved currents. Okay? So I'll give you again a simple example. So let's start from, how much? Okay, almost finished. Okay, so let's start from the unperturbed Lagrangian. So this is in the variable w bar. And of course, the equation of motion are the trivial one. Okay, Laplace operator applied to the field is equal to 0. And perform the change of variable. Okay, so this is a free theory. So you have actually a very wide possibility for choosing the conserved currents. Okay, so for example, you can take power of the derivative of the field or high order derivative of the field, etc., etc. So this will form different bases. So this actually at classical level, they will give you apparently different theories, but you expect that only some particular combination, this would give you the correct quantum theory. Okay. Okay. So let's for this case, let's choose the first. So this power-like conserved currents, and for simplicity, it's really this helps quite a lot because the positive S sector it's still very puzzling. But let's go in the negative spin sector. Okay? So if you do this in the negative spin sector, then the only part which is perturbed is the diagonal elements. So the tau appear only on the diagonal element here, and you are perturbing the theory diagonally. So you see in this place here you have the essentially the holomorphic part, which so contains only the derivative in omega. This is the anti-holomorphic part. So already at this point you see that this kind of perturbation is not coupling the right mover sector to the left mover sector. So it's a sort of a conformal transformation depending on the field itself. Okay? So we do this coordinate transformation, so you get a relation between the derivative in z and z bar and the derivative in omega and omega bar, and you have to solve this simple system, which is similar to the one shown by Carl Bender, but actually the solution of this system. So you see it's coupling only holomorphic to holomorphic and anti-holomorphic to anti-holomorphic. You invert this relation and you actually, as you can imagine, you get something complicated which actually can be written in terms of a generalized hypergeometric function. Okay? So this is the result of this of the solution of this change of variable here. Okay? Okay? However, since you are okay, so it's a solution of essentially you get it by solving this expression. I'll show you. I mean, it's coming back in the.
It seems to me that the derivative is on the right as well, inside the argument.
No, this is already the field already derived. Okay, so there is no derivative. So there is no action. It is what you mean. There is no action of this on the right. Okay. Okay, you can come back to this question after 2 minutes, okay? So this essentially means that the equation of motion of the deformed theory are again the free equation of motion, but in the variable z, okay? So these are the equation of motion. So we did something, we deformed the theory, but underlying the dynamics is still that one of a free theory, okay? And you can, of course, find the lever k or spin k Hamiltonian and the level k momentum by taking this combination where this ik and I bar k are defined in terms of the stress energy tensor component in this way. And you see that in this case, again, this ik and I bar k, they fulfill this simple equation. Okay? Okay? And I think at this level it should be clear that this is the solution of this equation is a generalized hypergeometric function. So the claim is that this perturbation. Okay, 2 seconds, yeah, well, 2 minutes. Okay, so the claim is that this perturbation, they break Lorentz symmetry, and to see this, let's see the effect. So we are still thinking about a negative S, see the effect of such a transformation of a simple solution, which is a vortex type solution, okay? So it actually happened that if you do the dt bar transformation, the solution goes to itself. So it's, the solution is invariant under the tt bar deformation. Okay, so you remain this vortex type solution, or staircase type solution, though you want to call. But if you go to s minus 1, then you see that a single log singularity here becomes split into, from this point, 2 branch points, square root branch point depart. So this is s equal minus 1. It's giving a more complicated Riemann surface, which is this one. As if you go to s equal 3, etc., you get more and more square root branch point. Okay. Okay. Just to finish. Moving from a local definition, this is the standard, this is the same as it happened for the tt bar perturbation. You can get all the equation we had, and using the idea of factorizability, you can replace density with average of the field in this way. So if you do this, you get this equation here. So essentially now it would depend on R, which is the volume. This is standard. This was already done by many people in the tt bar perturbation. And if you use this constraint here, so you think about this constraint as being involving quantum conserved charges, then you can easily find that this is the scattering phase factor. So it's completely asymmetry between theta and theta prime, where theta is the rapidity of one particle and theta prime is the rapidity of the other particle. Okay? So this is a pure exponential because we are thinking about the conformal theory, but if you, for a massive theory, this will be the sign of theta minus s theta prime. Okay? So once you have the Cdd factor, then essentially you have quantized the model, because you can put this Cdd factor in the nonlinear integral equation. That's a quantum, is valid at quantum level, etc., etc. Okay, I think I have finished.
Any question?
Yes. Leonardo?
So if you have negative integer spin, can you count how many branch cuts do you have? Like an example of 3 slides ago, maybe.
Yeah, it's, what was it? It was 2n, 2s plus 1 or whatever, you know, or something, yeah. But yeah, you can count. I mean, it's, yeah, for s, yeah, 2s or something. Yes.
So I want to ask a general question. So since the time derivative now goes very complicated way in the Hamiltonian, so what about causality, Hamiltonian picture, time evaluation?
Okay. It's quite complicated. I think we are not sure about that. So somehow you see.
You wrote down the space of state.
Yeah. So we wrote down the space of state and the same equation. Formally, we get it from so if you include this Cdd factor in the Destri-de Vega equation, TB equation, you get the formally the same equation at quantum level. Okay. However, at least this negative spin sector, it's very puzzling because the underlying dynamics is essentially free, while the Hamiltonian has been perturbed. So we think essentially that maybe this is not the Hamiltonian, the correct Hamiltonian description. So this charge evolve due to this the inclusion of this tau parameter, but the time they don't evolve anymore in the correct time. So they evolve in a different on a different time. Okay, this is I don't know. You can also check that you don't. So if you take this PS that I define with E plus minus E minus, they are actually not quantized. Okay, so this tells you that probably we are not looking at the really eigenvalue of the translational operator, okay, of the translation operator. But still, I think that description on the two sides, the classical part and the quantum part match completely, at least for this sector. So we are pretty sure that this Cdd factor are the only one that can be associated to a change of variable at the classical level. Okay.
Well, I understand this, but to have before this Cdd factor, you have to have a notion of stationary state, a notion of time evolution. So
yes.
You have to be sure that you have a stationary state.
Yes.
Okay, stationary states. So how do you know this?
Yeah, we didn't look at that. Okay, for us it was really yeah. But this charge are conserved. I mean, there is no point. I mean, this perturbed charge are conserved because they are, you know, you get one form and you do the change of it. Yeah.
It looks like you don't have two charges.
Yeah, but this is also a problem in the TT bar. Okay? Even in the TT bar, you have the same wave breaking solution. The answer is that. From a string theory point of view, is that you have just to change the parameterization. So the blob is very well defined. It's just you have to change the parameterization. So when so we asked this to people like Dubosc, and that's the answer. I mean, it's just the point of view. It's just the way of you parameterize the surface, which is not the optimal one.
So I think maybe that just answers my question. But naively, if I'm getting this, like when you have your kink which overlap, and if I'm a traditional PDE person, then what I do is I introduce a shock wave, make it single valued, and then look for weak solutions of the equation.
Okay, this is integrable. I mean, this is these are integrable model. You cannot expect that this is this is something you cut by hand. This your solution, which you spoil integrability, you spoil continuity, and things like that. Or at least differentiability. I don't know. We can discuss. Yeah, we didn't explore it.